of the week. Okay. So let's talk again about the wave resource. I made a brief introduction yesterday, but I will try now to make a resume. So, as you already know, the wave energy is a concentrated form of the solar energy. And what makes this resource interesting? Well, it's a clean and renewable energy, as you already know. Predictable output, not as in the case of tides, but at least in this case we can predict waves with some confidence 2 or 3 days ahead. So that's good because we can foresee what power production we are going to have. In addition, we have a different timing from wind and solar energy. For instance, during night you do not have sun, but you may have waves and produce energy from the waves. The waves are linked to the wind, but as you know, sometimes you go to the beach and you have waves without wind. So that means that those waves were produced offshore and have traveled several kilometers till the shore. So you can have waves and not having wind. So different timing is also an advantage if you want to have a good production. If you look to this graphic, you can see that the resource correlates well with electricity consumption, at least in the North Hemisphere. So we consume more energy during the winter, and we have more wave resource also during the winter because we have larger waves and therefore more energy. Power density is higher than in the case of the wind and in the case of the sun, and the resource available is very large, so we have several reasons to invest our time making research in this topic. Yes? Any question?
Thank you. So my question is, when you talk about resource availability 10 to 20%, is this like the effective resources?
Is what?
Like the effective, you were telling yesterday that there are like the effective resources, the one that we are allowed to harness, and there are the total.
Yeah, because we can assess, let's say, the theoretical global resource, but we are not going to be able to harness all that energy.
Yes.
Because the technologies have a limited efficiency that is far away from 100%, and there are some places where we cannot install the technologies. So this is, let's say, an estimation of the resource we can get, okay? Because the overall theoretical wave resource is more or less the same as the worldwide electricity consumption. But if you take into account the efficiency of the technologies and some restrictions in terms of installation of the device, maybe you can harness 20% of the electricity consumption in the world from the waves.
Okay, thank you. But for example, when you estimate this, because I think that it should be very difficult to estimate because every country has different rules of...
yeah, it's very difficult, yes.
So it's more or less a rule of thumb, I guess.
There is a lot of uncertainty in all these figures. And sometimes if you read different works, different books, you see different figures. Here what is important is to have a rough idea of the potential available, but no one knows exactly the effective number. Okay? And we cannot predict also what will be the efficiency of the technologies 10 years from now, because that depends on the research that is going to be done in the next years. So there are uncertainty in the theoretical resource, also uncertainty on the efficiency of the technologies, and also uncertainty in the locations where the devices can be installed. So it's just to give you an overview of the potential that is available. Okay?
Paul, what's your definition about power densities? Power per area?
Yes.
Yes?
Yeah. So that means that we can harness the same amount of energy with smaller devices.
Okay.
So that's the main explanation, or the main consequence of that point.
Okay.
In terms of wave energy, we can divide the wave energy into main components. So the kinetic energy, because we have the water particles moving in a circular orbit offshore or elliptical orbit near shore, and we can assess that energy using one of these expressions. And we also have the potential energy that is related with the up and down motion of the sea surface. So that's the important point I want to transmit here. We can also assess the energy flux across a vertical plane parallel to the wave crest, so a plane like this one, in this case with a 1 meter wide, and the energy flux per unit length can be assessed using this expression for regular waves. In this case, you should put here the wave height and here the wave period. Or if you have irregular sea state characterized by a significant wave height and an energetic period, you can use this expression here to assess, let's say, the mean energy flux across that plane. So what we can see here is that that energy flux or power depends on the square of the wave height, or in this case the significant wave height, and also depends on the wave period. Okay, and it represents the energy flux from the sea bottom till the surface. Okay, so that's the total resource that is available. It's also important to mention that there is a variation like this one of that quantity. So we have more, let's say, power to harness near the surface than in the bottom, because the water moves more in the surface than in the bottom. So that's why most of the devices are floating devices at the surface. Okay. Some comparison between waves and wind. So in the case of the waves, most of the wave energy flux is located nearby the surface. So most of the devices are installed here, except some technologies that were developed for shallow waters, because in that case this variation is not so large. And in the case of wind, we have this profile, and we have here the turbine that only captures the energy of a teeny sublayer of that profile. Okay, so in theory, a wave farm can absorb a large part of the wave energy flux, since most concepts are floating at surface and most of the energy is nearby the surface. The energy flux per unit vertical area for waves near the surface is about 5 times larger than for wind and much higher than for sun. So it's a very concentrated form of energy. So that means that for the same rated power, we can have technologies with smaller dimensions. Well, I already mentioned that in medium terms in Portugal, we have about 40 kilowatts per meter of wavefront. So in a 2 meters wavefront, we have the same power of a regular car. You already seen this picture, so the distribution of wave energy in Europe. So the Atlantic coast has a good resource, the Mediterranean less, because waves are smaller in the Mediterranean, because in the Mediterranean the fetch is smaller. The overall perspective in the globe, and well, you can see here that the theoretical potential available is very similar to the electricity consumption in the world. But of course, we cannot harness all that theoretical potential because of the reasons I already explained in the beginning of this session. Now, moving to the technologies, and going back, in some books you may find some references to some initial and primitive utilization of wave energy in China a long time ago, but the first prototypes tested in the sea were tested by this professor, and that is from Japan. In terms of technology and we have, as you already know, several technologies, so with very different working ideas. So it's a very different situation if we compare the situation of the wave energy with the situation of the wind energy. So we have more than 1,000 patents, more than 100 concepts being developed, and perhaps several dozens of devices tested or being tested in realistic conditions in sea. So we have a wide variety of technologies. Here you can see some tentative to group those concepts. We have this type of concepts. They are called attenuators. So we have two floating bodies, one articulation, and they move that way as the wave passes through them. We can also have point absorbers with a floating part on the sea surface, move up and down as the wave passes nearby. These oscillating wave surge converters, so these ones are installed in the sea bottom. So these technologies are only suitable for shallow waters, because if you install these in deep waters near the floor, you don't have almost energy to harness. You also have the oscillating water column. It's a very well-known and well-studied technology. I will talk later about some applications of this technology in different parts of the world. We also have the overtopping devices, so devices that work taking advantage of the wave overtopping, that phenomena that I mentioned in the previous lecture. The submerged pressure differential. So we have a difference in pressure when the trough and the crest passes above this type of devices, and we can harness energy from that. We also have this complex device called the bulge wave technology. So there is a bulge that is created and moves along the device from the stern part to the head. And the rotating mass concept. In this case, we have, let's say, a hull with something inside that moves when the waves pass. And in this case, we have all the critical components of the technology well protected from the sea inside that hull. Yes?
Hi, my name is Larissa. I'm from Brazil. I wanted to question about the oscillation wave surge. Is there a limit for the depth so the wave can move it? Because it's, from the GIF, it looks a little bit below the sea,
Yeah.
the waves. So it can't be like too deep, or and it can't be like on the surface because it wouldn't completely move. Okay, so is there I don't know, a value, an optimum value for this technology?
If you analyze the motion of the water particles, if you go deep into the ocean, you don't have motion. You already know how to calculate the wavelength. If you divide the wavelength by 2, below that depth, you have almost no wave motion. So in that case, the device doesn't work. So you should apply this device near the coast, where you have almost all the water column in movement. You should not put the device very close to the surface. As far as I know, the applications are more or less in water depths of about 20 meters. But you also need to take into account the tidal range, because in some parts of the world, the tidal range may have 2, 3, 4 meters or even more. So I think a good reference is something around 20 meters, maybe a little bit more, but of that order of magnitude.
Thank you.
Hi, my name is Raymond from California. So the overtopping devices look like they would be kind of challenging to build with the constant bombardment of waves. Is there an approach or a technique that they use to construct them?
Can you repeat the first part of the question?
Yeah, so building the overtopping device seems like it would be difficult because you constantly have the ocean.
Oh, no, I think that is not a problem. There is a lot of experience in building breakwaters and the coastal structures, so the same techniques can be applied. And you can also build the models on land and then put the models together in place. So in terms of construction, I think it will be maybe a little bit more complex, but do not much different from the construction of other coastal or harbor structures.
Okay, thanks.
And there is also some applications in real structures. I will present you later some examples.
Thank you.
Thank you. I would like to know, looking at these devices, I'm asking myself, what is the power generated So I think that this is just a concept, so they
Yeah.
can be smaller and bigger, but just to get a feeling of how much power can you generate. And also, do you store somehow energy, or do you put cables?
Yeah.
to-
Well, the power that is produced depends on several variables. It depends on the dimension of the device. It depends on the efficiency. So what you have here is just a tentative to present the different concepts. But within each one of these categories, you may have several dozens of technologies. Okay, I will present later some examples of some of these categories. Regarding the second part of the question, the idea is to install these devices in a wave farm. So offshore, you can install several devices, 50, 100 or so, and then you need a cable to transport the energy from offshore till the shore. Okay, that's more or less what is done with offshore wind parks that are currently in operation. So you need a submarine cable to transport the energy from the wave park and to connect that to the grid. Okay.
I think that I will interpret your question. How can you absorb the energy of the waves and transforming mechanical energy, and
Okay.
after transforming energy, electrical energy?
Okay.
I think that is your question. How can you transform a wave energy in electrical energy, or storage this mechanical energy to
Yeah,
transform?
I will try to talk about that later when I
Okay.
present the different technologies. I think it's better because I have some figures that help on the explanation. And I have also some slides about the power takeoff systems.
Because do you have a linear movement, circular movement?
Exactly, yeah. In this case, low head turbines. You see, so depending on the technology, we have different types of power takeoff systems.
Hello, my name is Diana. I'm from Colombia. I would like to know of all the devices that you present. I think, I don't know what you call in English, I think the wave dynamic, that do you prefer or do you think it's better? Because I think that is a lot of different geometries. So what do you think which is the best geometry depends of the
Well,
wave characteristics
yeah.
to produce more energy?
Well, it's a difficult question, and I think nowadays no one has answered to that question, because what we know is that there are several concepts that work. They are able to produce energy. And it is also widely accepted that in the near future, we are not going to have a convergence to a single technology, like it happened in other energy sectors. So I think we should expect, even in the future, the existence of several concepts, each one suitable for different applications. Okay. But at the moment, I think there is. Well, I think we are not able yet to choose the best one, because some have some strong points, also some drawbacks, and it's difficult to compare them because they are very different.
So, can you just explain, for example, the first one, it's better for waves going long.
Yeah.
I don't know.
But
this
for
kind of thing?
instance, if you intend to build a port to create good conditions to the mooring and berthing of ships, you need to build a breakwater. You can take advantage of the structure and to install in the structure a wave energy converter. In that case, for instance, it will be a good option to install this type of device. so an overtopping device, because you have a structure, you can build the ramp in the breakwater to create the reservoirs and take advantage of the wave energy in that case. It will be more difficult, for instance, to install these or these there, okay? But, or even these. But you can also install an oscillating water column, because you may use in the breakwater construction a caisson, so a box of concrete with some holes inside, and produce energy that way. So depending on the applications, there are different technologies that may be suitable and others that may not be suitable. So it depends a lot on the application you want to do, okay? So we know that we have a wide variety of concepts, each one with a specific performance. The idea of this slide is not to present, precise values of efficiency. It's just to give you an idea that efficiency depends a lot, not only on the concept, but also on the developing stage of the concept, okay? We can also classify the devices taking into account the distance to the shore. We may have shoreline devices that are integrated in coastal structures or in harbor structures. We can have near-shore devices in intermediate water depths, or we can have offshore devices, usually floating devices. We can also classify the devices taking into account their dimensions and orientation. In this case, we have an attenuator, so it is aligned with the direction of wave propagation. We can also have a terminator. In this case, you see the wave is propagating in a direction that is perpendicular to the terminator. We may have a large absorber, so a device with large dimensions when those dimensions are compared with wavelength, or a point absorber, a small device compared to the wavelength, or we may also have groups of point absorbers, okay? So it's a different way of classifying the technologies. The other way is taking into account their working principle. And in that case, I think we can divide the concepts in three main categories. The oscillating water column. I will present later some details about that concept, so how it works. And that concept can be installed in floating structures or fixed structures. Okay? The fixed structure could be, for instance, a breakwater, as I mentioned before. We may also have oscillating bodies, floating at surface or submerged, taking advantage of the heave motion, pitch, heave, or bottom ingot. Okay? So heaving is the vertical motion of a floating body. Pitching is this motion like this, okay? Regarding overtopping, we may also have fixed structures in the shoreline or integrated in breakwaters, or we may also have floating structures, so in deep waters. You have here some names of technologies that were developed for each one of the categories. The names that are marked in red are technologies that at a certain stage of their development were tested in upward wave basin. We have here, for instance, the wave cat, the wave roller, and the core power. So, because since the first idea till the installation in the sea, there are several research stages, and it's very important to make experimental tests on a small scale to see how the concepts work and to improve them. And these three were tested in our facilities. I will present more details about those technologies later in the presentation. So we have a wide diversity of concepts, as you already know, different shapes, different dimensions. So the main question here is how to reach the economic viability. Okay, so that's the main question. As I presented yesterday, the levelized cost of energy, of wave energy, is higher than the cost of the other resources. But we should take into account that in the learning curve, we are in a very initial stage. So in the future, we should expect a reduction of the energy costs. And it's also important to mention that we usually think or we usually have into account the cost of the energy for onshore applications, okay? But we also have some activities in the middle of the ocean that require energy. And it's not easy to transport the energy from inland to those offshore locations. So one good option could be to harvest locally wave energy to give the energy needed to those offshore activities. In that case, maybe it is better to reach, let's say, good economic conditions for the installation of these concepts. So it's a different way of thinking that should be also taken into account. It's not working. Okay, so one interesting application is the application of wave energy converters in harbor structures. Because there we have resource, because harbor structures are built to protect the inner parts of the harbor from the wave action. So we have resource there. And we also have infrastructures with or infrastructures that need energy to operate. So the ports need energy for all the port activities that are carried out within them. So we have, let's say, a convergence of renewable resources and consumption. And it's also a good opportunity to change the usually negative public perception that the persons in general have about ports. So ports could take advantage of this technology and produce locally renewable energy for their own consumption, that way reducing greenhouse emissions and air pollution. But not all technologies are suitable for that kind of applications. From all those concepts that I've presented before, the most suitable ones perhaps are these two. So the overtopping concept and the oscillating water column. They are not the only ones, but in a first guess, they are good options for the installation in breakwaters. The main advantage of this combination, so the combination of wave energy converters with breakwaters, is that the intervention costs can be shared. So if you are going to build a structure to protect the harbor, you can take advantage of that and by somehow extra expense integrate in that structure the wave energy converter. In addition, in this case, you have the grid nearby, because you have the grid of the port. So you can adapt the grid to receive that energy. You may also promote water circulation in the port. One usual problem is the reflection from the harbor structure. So the wave hits the structure and is reflected back. That is bad because the reflected wave may disturb the ships entering the port or even inside the port. And if you are installing a device to absorb the energy from the wave, you may at the same time improve the hydraulic efficiency of the structure in what concerns the reduction of reflection. Okay? And of course, it's also an opportunity to integrate what we call the blue energy in those structures in order to transform them in more sustainable infrastructures. So there are several possibilities. One of those possibilities is the use of overtopping devices. This animation shows the sea wave slot cone generated integrated in a sloped structure. So essentially here what we have is a ramp and several reservoirs that receive the water that runs up in the ramp and reach those reservoirs. In this case, we need a vertical duct with low head turbines installed to transform the potential energy of the stored water into electricity. So, yeah.
Good afternoon. My name is Felipe. I'm from Bahia, Salvador. I have a question that in Ceará, here in Brazil, we have a mechanic arm that floats in the water, and I would know why you are not talking about this kind of technology. It's obsolete,
No,
or what happened?
Not talking until now, but I have I have also a slide with a figure that shows that application. So these are perhaps the most suitable ones from my perspective, but there are also other possibilities. Okay, so sometimes not talking anymore. So sometimes it's important to take into account several possibilities and then to choose the best ones. But in fact, there is a real application, or there was a real application in a breakwater here in Brazil. Another different concept. So we have here also the breakwater, a ramp, a reservoir, and here the turbine. So it's a more simple concept. Sometimes the simpler ideas are the best ones. And here a real application in Italy, in the port of Naples. So they were able to integrate a pilot device in the breakwater of Naples, and they are carrying out some tests presently to assess the efficiency of this overtopping based energy converter in that breakwater. They have they call that technology the OBREC, overtopping breakwater for energy conversion. So it's in operation since 2016, and I think I don't know if I have that information here, but it's not much. But they don't have yet the turbines installed. They are planning to install them in a short time, but they have not yet installed the turbines. But since it is a small and pilot installation, the power will be small. We have also some real scale installations in breakwaters of devices based on the oscillating water column principle. We have here the port of Mutriku in the north of Spain, so more or less here. You see the breakwater, and here the location of the wave energy converter model. So in this case, we have a set of turbines, and the total capacity is nearby 300 kilowatts. So it's a demonstration pilot station that was installed in these breakwaters. Here you can see the impact of the wave in the structure. So the breakwater at same time protects the harbor and produces energy. Okay, I think from here you can more easily understand how these oscillating water column concepts work. So we need to build a chamber. The chamber you can see here. We have here the seaside. So when a wave approaches, in particular the crest of the wave, what happens is that the free surface here goes up. Okay? And when it goes up, the space occupied by the air reduces, so there is a compression, and the air is forced to pass by a pneumatic turbine. Okay? After the crest, we have the trough of the wave. The water here goes down. There is a decompression of the air, and the water enters from outside to inside the chamber. So we harness the energy from the air motion, not only from inside to outside, but also in the other way. There are some turbines, the Wells turbines, that work in the same direction, regardless of the direction of flow. Okay? So from this, I think you easily see that is a structure that can be easily integrated in a coastal structure or in a breakwater. And in this case, you can also see that the most, let's say, critical components, the core of the technology, is above the water level. So it's not in direct contact with water, what is good due to the aggressivity of the seawater. There are several applications, not only in Europe, but also outside Europe. And you can also see here some important components, like a valve that is important when we have the impact of very large waves. In order, it's let's say a relief valve to avoid problems in the turbine. Okay. So it's a concept with several applications worldwide. One of those applications was in Portugal, in one of the islands of Azores archipelago. You can see here the oscillating water column, and here a wave eating that structure. That installation was working since the end of last year. So between 2004 till 2017. Here a video that explains in more detail how these concepts work. It was produced by a company, a large company that produces turbines, Void. I don't know if you know that company. And it refers to an installation near the coast. So you can hardly see the device. It's well integrated in the coast. is a concrete structure. You see the underwater entrance to the chamber, the wave, and the water going up and down inside the chamber, and the flow of air through the turbine, not only from inside to outside, but in the other way. So it's a very simple concept. You see that the turbine is rotating in the same direction. The direction doesn't change when the flow changes direction. Yes? Well, well, the idea was to build a pilot demonstration site and to get some better knowledge of the operation of those kind of systems and to test, let's say, strategies to control the turbine and to integrate the energy in the grid and so on. And after some time, they decided to abandon the structure because they needed a huge amount of money to rehabilitate the structure, because it was in operation since 2004 till 2017, so about 13 years.
I'm Gabriel from Argentina. I just want to know what's the velocity of the air that joins the turbine.
Well,
It's just a rough number.
well, I don't know how to answer that question, but well, it depends on the dimension of the chamber and the air duct, and also on the wave, because different waves impose different motions of the air inside the chamber. So, but I don't know a figure. I don't have a figure to present you.
Just a quick question. I was wondering, the 400 kilowatt power, it's actually always changing, right?
Yeah. So
Depending on
there is a rated power,
Mhm.
but usually the mean harnessed power is much smaller than that value.
Okay.
So, but the system was prepared for that maximum power, but in average terms, maybe 8 times less or so,
Okay.
because the wave characteristics change a lot, and the power of the wave depends on the square of the wave height.
Okay.
Okay.
How much is the pressure ratio between the inside chamber and the outside?
Well, it depends on the design of the chamber and the turbine. So and those figures depend a lot on the geometry, on the application. So I cannot give you a precise number, okay? Because they depend on the application. Okay, let's move.
My name is Bruno from Angola. I think one of the challenges African countries in general face is the energy. Just to give a figure, in Angola, all 5% of the population have access for energy. In your presentation, never talk about this kind of project in Africa. I don't know if there is such project work in Africa, and I would like to know: is that possible to have like several countries working the same project? For example, there is a region in Africa that we call Great Lake. It's including Angola, Mozambique, is it? Mozambique, Zambia, and so on. That countries that share the same. I think they share the same. The same ocean, isn't it? Yeah, same ocean. Is it possible and feasible to have like a project to help to solve this problem that Africa has? Energy.
Well, I think it's important to have in the energy mix of any country a large share of renewables. But I think that the best share depends on the country. And may be different, so it may be different from one country to the other. Well, maybe in the case of Angola, you have other resources more important than wave energy to use to produce energy. But of course, it is possible to have, let's say, international collaboration to develop a specific technology. But perhaps you may have other more important resources and issues to solve than maybe to work in that type of things. Okay, and in case of Angola, I think you have a lot of energetic resources that you can use. I don't know if I was able to answer your question properly. Okay.
Sorry, I have one more question. From the technologies you presented us, it seems that the concept is pretty simple. It's just the concrete structure and a turbine. And I was wondering what makes this technology so expensive and the energy so expensive?
Well, you need to build the structure in concrete. You need a good turbine, some equipment related with the energy conversion and integration in the grid. And the efficiency is not 100%. It could be 15%, 12%, 20%.
Yeah, but it's the same for wind energy. And
yeah, but in the analysis, you should take into account everything, the energy you produce and the costs of the structure. And if you take into account everything, you get presently that type of figures, okay? But you should also take into account that sometimes you have a very marked scale effect. So if you produce one turbine of that type, you have a cost. If you produce 1,000, you have a very different costs. So I think that with research, with that scaling effect, costs will go down. Okay, but presently they are higher than the cost of other resources.
Okay, so from my understanding, all these turbines that are implemented in these projects, they're specifically designed for this case.
Yeah. So they are pneumatic turbines designed for this kind of applications. Okay, and also an important aspect is the maintenance costs, because this type of equipments are exposed to very variable forcings. So since the waves change a lot, also change the loading on the turbine and all the systems inside the chamber. So you have high operation and maintenance costs, and that is also one of the reasons why the energy produced this way is more expensive than the other way. Okay, so if you put everything together based on present figures, you have higher costs, the costs I presented yesterday. Okay, so you have several other concepts installed in several places in the world based on floating elements. Well, this is just to give you a quick overview on those concepts. So very different. In this case, for instance, we have a concept that is also based on the oscillating water column principle, but in this case is installed in a floating structure. So the base is the same, but instead of a fixed structure here, you have a floating one. But you also have here the oscillating water column and the air turbine over there. This one, I think, is a very well-known concept, the Pelamis. It was tested in Portugal in 2008 and later on tested again in this place. But unfortunately, the concept did not succeed and the project was abandoned, at least in Europe. So you have these floating elements connected to each other by articulations. So a lot of money was spent in this case, but sometimes we need to test to see if things work or not. But if you go to Google Earth, at present you can see some parts of this device stored inside the Port of Leixões. They are parked there. The Port of Leixões is the port, is a port nearby the site where the Pelamis was installed in the Portuguese coast. So it's a device, it's a floating device, multi-body, based on pitch and yaw. So this was the Pelamis, but now there are some, there is a Chinese company that is working in a similar concept. So the project was stopped in Europe, but there are some people working in the concept. Maybe they will get better results in the future, I don't know. Here we have the WaveCAD concept. So in this case, we have two hulls articulated here. And this concept is based on the overtopping principle. So we have several reservoirs in both sides of the device. And so since we have this shape, there is a concentration of the wave that facilitates the overtopping. So we have several reservoirs with turbines that transform the potential energy into electricity. This device was also tested in our installation some time ago. Here we have the wave roller. So a bottom fixed wave energy converter. So you have an articulated paddle that moves under the wave action. It was tested also in our wave basin, but now it is being tested in the Portuguese coast in a place called Peniche. You can see here the model we have tested, so a very initial model of the technology, but it was very important to understand better how it works. Okay, so the company that was developing this concept was a company from Finland. It was installed in this beach nearby Peniche in the central part of Portugal. Well, here you can see our basin and the WaveCAD model. So that device based on the overtopping principle I presented before. So the two hulls, the articulation here, some pumps here, and a system to measure the motions of the device in its 6 degrees of freedom. Another device a point absorber with a buoy at the surface. This was also tested some years ago, maybe 4 years ago, in our wave basin. Since the maintenance costs are usually high for this kind of technologies, because they are in a very aggressive environment, there are also some technologies that try to protect the most sensible parts of the equipment inside one hull, like in this case. So the idea is to protect the power takeoff and all the instrumentation and the equipments here. You have here the penguin, so it's a an eccentric rotating mass. So due to the oscillations of this, we have the mass rotating inside the hull in order to produce electricity. So you can see here some tests in the sea. Here a similar concept, at least they share some characteristics, but in this case a gyroscope is used, so a more complex system. This is being developed by a team from Italy. We have here the Wave Star. Is a concept similar to the one that was tested here in Brazil, but not exactly the same. In this case, we have some floating bodies connected by these articulated arms to a fixed structure. So the wave passes through the structure and those floaters move up and down, and it's possible to harness energy. And if the wave conditions are very energetic, if we are facing a storm, it is possible to raise those arms and to protect the floaters from the loading. So it's very important to have good efficiencies for operational conditions, but also to survive storms. So the survivability is also an important topic for this kind of technologies. Other possible installations from Denmark. And here you have some tests of the system that was installed in that port in Brazil. So it's not much different from the other one, maybe the shape of the floaters and some details in the arms, but in general they are quite similar. Yesterday I presented some testing places in some countries. Here you can see that there are other places where the devices can be tested in real sea conditions. In Portugal, Spain, England, etc. So several testing sites. And regarding the power takeoff systems, we can group the power takeoff systems in several groups. Yes?
I was really interested in the equipment with the gyroscope. Can you explain how it works, or can you explain a little bit more details about this
Well,
equipment?
it's not easy to explain how a gyroscope works.
No, it's not the gyroscope works. How works the equipment with the gyroscope?
Essentially we have a floating body with let's say a hull with the gyroscope inside, and so the waves induce some motions of the floating platform of the hull, and those motions have energy that goes to to the gyroscope. So the oscillations of the floating platform also induce motions of the gyroscope. So the principle is more or less the same as in the previous case. But in the previous case, you have an eccentric mass. So a mass, a large mass inside the hull, and since the platform is moving, the mass inside is also moving. Okay, and you can have a power takeoff to remove energy from the motion of the mass. In this case, instead of the mass, you have inside that floating structure a gyroscope. I don't know if I have here, but yeah. So this is how a gyroscope moves. So this disc is rotating, and you remove energy from that rotation. But to explain, well, I think it's better to see it than to than to explain it. So, but this motion is induced by the oscillations of this. So this is a floating body, okay, that moves under the action of waves. Okay.
Because I think that it will be like really interesting, and like have this more, maybe can I don't know, like have more what do you say, like you can get more energy or something like this.
Yes, but sometimes well, it is important to harness a lot of energy, but the most important, I think, is to produce enough energy to pay the installation, to pay the maintenance, and to give some profit. Okay? Sometimes it's better to produce less energy and to have some profit, to produce a lot of energy and not having profit. Okay? So in this case, usually you have smaller efficiencies, but the operation and maintenance costs are usually smaller because all the critical parts of the devices are protected inside the hull of the platform. Okay, so at the end, the most important part is to have profit. Okay.
I have one more question. As I saw from all this technology, the technologies, they are standing, and I was wondering whether it's possible to attach technology that harvests the wave energy to a moving body, for example, to a boat.
Yeah. Well, several options are available. It is possible to build hybrid systems to couple some wave energy converters with offshore wind turbines. What is possible. It's since the boats traveling the sea also have some motions, it is possible to install small units inside the boats and produce some energy for local consumption. So a wide variety of possibilities are available. Okay.
Yeah, but because I was thinking like maybe when you attach them, then you will need more energy to carry those things.
Yeah, but in this case, I was not considering the attachment. I was considering putting some, for instance, you can put this, a smaller version, inside a ship, and you can produce some energy for the radio, for communications, for local consumption. So you are using wave energy, let's say, to give some power supply to the ship. Okay. So a lot of possibilities are available. So in terms of power takeoff systems, you may have linear mechanical systems, you can have hydraulic power takeoff systems, oscillating water column systems, overtopping systems, and rotary mechanical systems. So the five main categories of power takeoffs. So in this case, and if we are studying the technology, we can assess the power by measuring some force and velocity. So we need to measure loads and motions. In this case, in the case of hydraulic systems, we need to have information about the pressure and the flow in order to obtain the power in this kind of power takeoff systems. In the case of oscillating water columns, we should have also information about the flow and the pressure. We can calibrate the system in order to have a relationship between the pressure and the flow, and in that case we can obtain directly the power from the pressure. In the case of overtopping devices, so we need to know the head, so the difference between the water surface in the reservoir in relation to the mean sea level, and we also need to know the mean overtopping flow rate in order to assess the power. And in this case, in the case of torque and rotational systems, we should measure the shaft torque and the angular speed. So different power takeoff systems, different ways of reproducing those systems in the models, and different ways of estimating the power that is produced. So regarding the power absorption, so how can we assess the power that is harnessed by a specific technology? So first, it's important to characterize the wave resource. So we should characterize the region in terms of offshore wave conditions, in terms of bathymetry, and then to propagate the conditions from offshore till the location of interest using proper numerical models. In this case, the location is here, okay? So we have deep water wave conditions. We should be able to propagate the conditions offshore till the shore, okay, in order to characterize the wave resource in the place of interest. Since the wave propagation is affected by the water depth, we should know the bathymetry in order to properly simulate the propagation of the waves from offshore till the shore. And here we can see the wave power around the region of interest. I choose this example because you can see very easily that three nearby locations, A, B, and C, have quite different wave conditions. So from the same offshore wave conditions, due to the influence of bathymetry, here we have different wave climates in position A, B, and C. You can see that by seeing that the colors are different. So we have different power levels in those regions. Or you can also see that if you analyze these power metrics that present the the resource available on the free locations. So it's very important to take into account the influence of the bathymetry when studying the wave propagation. So making this type of study, you are able to characterize the resource that is available at the installation site or at the site proposed for the installation of the wave farm. But that is only part of the problem. Okay? You also need to know the performance of the device. So you need to know, for instance, for different wave periods, which is the efficiency of the device converting the energy of the wave. Okay? Like a curve like this. Or more usually, a power matrix of the device that presents the information not only in terms of wave periods, but in terms of wave periods and wave heights, because the efficiency may depend on both parameters. Okay? Then, if you combine the resource matrix with the power matrix that represents, let's say, the performance of the device, you can assess the power production of that wave energy converter in that specific location. Okay? So at the same location, different devices produce different amounts of energy, because different devices may have different performance. Or on the other hand, the same technology in different places may have quite different energy productions, okay? Because different locations may present different resource matrix, okay? After combining that, you have the captured energy. If you combine the power matrix with the resource matrix, you will get the captured power or the captured energy, okay? In this case, what we did was to characterize the resource along the Portuguese shore, and then for a specific wave energy converter, what we did was to combine the efficiency or the performance of the device with the wave conditions in order to see along the Portuguese coast which were the best locations for the installation of the device. Okay. Any question before moving to the last part of the presentation? Yeah, different types of software. For instance, if you, well, for the first part of the problem, let's say to make the propagation from offshore till the proposed site for the installation of the wave farm, you may use, for instance, SWAN. Is an open source software that propagates wave conditions from offshore till the shore. It's a very typical approach because the software is free. Regarding the other part of the problem, well, it depends on the technology. In this case, since we were working with a floating device, and since we need to carry out several simulations, we have applied Aqua. Is a boundary element method based on the potential flow theory that gives you results in due time. We could also apply a CFD code, but it will take much time to get to the results. So we have applied a more, let's say, quick approach. But in spite of that, the simulations take some time. So maybe we are able to take 1 or 2 simulations per day. But it's much quicker than applying a CFD code. In this case, it was not required, but we have a cluster in the university that can be used. But it is mostly used to carry out CFD simulations with open foam and that kind of models. For Aqua, it is sufficient to have a computer with, well, a good RAM and a good processor.
Hello, my name is Frank, and I would like to know, how do wave energy converters deal with frequency? Because waves have low frequency, and if you need to convert it to commercial electrical frequency, there is going to be a big relation in the order of hundreds. So do they use gearboxes or electronic type of conversion of frequency?
Well, I think, well, I will try to answer part of the question, and I think I'm not able to answer the second part, because that is more an electric problem than an hydraulic problem. So regarding the frequency in terms of, in hydrodynamic terms, usually we have, let's say, an efficiency curve with a peak. So usually the devices work better for a certain frequency. If you move away from that frequency, the efficiency goes down. Okay? So if you are designing or studying a wave energy converter for a specific location, you should try to adapt the technology at least to have, let's say, the best performance for the frequency of this state with the highest amount of energy. In simple terms, I think that is the approach. Okay? In some devices, it is possible to change some characteristics in order to change the performance curve. For instance, we are working with a device that is based on the oblique motion of two lateral mobile models, and we can change the resonance frequency of the device by changing the angle of that motion. So it is possible to tune the device by changing the inclination to have the device working properly for the wave conditions we have in a specific moment, because we cannot control the wave conditions, but we can at least try to adapt the wave energy converter to have the highest absorption of energy. In other cases, it is possible to change, for instance, the weight of the device by putting some extra water ballast to change the response of the device, again with the intent to put the device working well for the conditions you have at that moment. I think your question was not exactly about this, but how or what we do with the energy we have. Well, but is not my field of research. What we do in our lab is to use very simplified systems and to use some resistance that dissipate the energy that is produced by the wave energy converter. I think it's not a simple topic because since the waves are very irregular, the motions of the devices are also very irregular, and also the output from the power takeoff system. Okay, and that is not good for the grid. So we want to have a smooth power curve. One thing that we are planning to do in the near future is to use supercapacitors to absorb the peaks, but that is an option for the experimental tests that we intend to do in the near future. But I think for real applications, in that case, the problem is much more complex, and I think I'm not the best person to answer that question. But it's also a very important point to smooth the power output from wave energy converters that are typically very irregular. Okay, any more questions? No. So some more slides to show some projects. Some projects we are running. So in the initial slides I have presented you some converters that were tested in our lab. Now I'm going to present some projects that are being carried out right now only in topics related with marine renewable energy. So this is our lab. It's a lab with a wave basin with dimensions not very different from the ones you have here. We have a wave maker that is able to produce regular and irregular waves, and also short crested waves. So that waves in which the wave crest is not long, so it's short crested. Here you can see that device that is based on the motion of two lateral mobile models. So by changing the inclination of this motion, we can change the response of the device, and we can tune the device in order to put the device working well for the conditions we have in the sea. So we work very fast in our facility, as you can see here. So we are able to produce and to build very quickly the models. Here we are installing a breakwater in our facility. Well, it requires a large quantity of material, but well, to have good results, it's very important to build very good models. So as I will present you next, we have some project that is related with integration of wave energy converters in breakwaters. So what you are seeing there is the reproduction of the breakwater geometry. So we need a lot of rocks. Well, that breakwater is almost 6 meters long, 3.2 meters wide, I think, and the height is about 80 centimeters. Okay, so it's very important to take advantage of these experimental facilities to test in a small scale the integration of the devices in the structures. Now some slides about SECO. We have a project that intends to develop this concept, a project funded by the Portuguese Foundation for Science and Technology. So we made some numerical studies using the Aqua software. So it's a panel method, and the software was calibrated using experimental tests. So it's very regular or very typical, the combination of physical and numerical modeling, what we call a composite modeling approach. So we make some experiments, we obtain data from those experiments that is then used to calibrate and to validate the numerical models. Once we have the numerical models validated, we can use them to study in more detail the response of the technologies, because it is easier to make things numerically than experimentally due to the large amount of work that is needed to build and to run an experimental model. Regarding hybridization, well, this is just it's just a presentation of some ideas. So we could integrate our wave energy converter with an offshore wind turbine. So in that case, we have the same supporting structure that is supporting the wind turbine and the wave energy converter. So in the same physical space, two technologies working together. We can have wind, we can have waves. So in that case, I think we can have a more even, a more uniform power output. Some studies carried out to assess the wave resource in the Portuguese coast in the winter time. In the winter we have higher waves, so the resource is higher. Spring, summer and autumn, so there is a seasonal variation of the wave conditions. And here some assessment of the power production along the Portuguese coast. This is a project that is running, an international project with several partners, from these ones from Porto, but also from Spain and from Belgium. And the idea is to develop solutions that could be integrated in breakwaters in order to transform the ports in more sustainable infrastructures. The idea is to analyze the possibility of giving the port, if not all, at least part of the energy that is needed for the port activities. Okay? And the innovative part of this project is that we intend to combine two different concepts to harness energy. So it's not an hybridization combining technologies for different resources. The idea here is to combine different concepts to harness wave energy and to integrate them in a single model. So that's the point here. And we have two case studies, one in Porto and the other one in Las Palmas. The idea is to have two representative ports. In the port of Leixões, we have a rubber mount breakwater, and in Las Palmas, we have a vertical breakwater. So we are developing solutions for different geometries of breakwaters. Okay. Another innovative project is this one, iNanoEC. So innovative nanotechnology for wave energy conversion. So the idea here is to take advantage of the properties of some triboelectric materials that when they are in contact with each other, they produce some energy that can be harvested. We are in the beginning, so I don't have results yet to present. So the kickoff meeting was about 3 weeks ago or so. But it's a very innovative project. We are seeing the potential of this kind of applications. For instance, to provide power for equipment that is deployed offshore. So it's very important to have a good monitoring network, measuring the wind conditions at sea, measuring the wave conditions at sea, and that equipment needs energy that can be provided by solar panels or by other means. And sometimes it's not easy to have energy locally, so we are trying to develop solutions that could harness wave energy to that purpose. We are also working on solutions to prevent scour problems in offshore windmills. So the offshore wind sector is a very dynamic sector, already in a commercial stage. There are several parks with several wind turbines. The idea here is to analyze the scour and to optimize the scour foundation. We were involved in this project, also in collaboration with several partners from Portugal, Belgium, England, and Germany, carried out in a large-scale facility. And the idea here is to understand better how dynamic protections work and try to optimize the design in order to reduce the costs of the foundation protections. Well, in terms of challenges, I have already mentioned some things about this. So this is related to your question. So we have a very regular power output. So it's very important in the future to transform this in a smooth signal. This is the result of the large variability of wave conditions in different time scales. So wave characteristics change from one wave to the other, from one day to the other, from 1 week to the other, from different seasons. So there is a huge variability on the wave characteristics. Well, it's also important to be prepared to deal with harsh maritime environment. So we have very large waves sometimes, and the seawater is also corrosive, so we should be able to handle those issues and also to deal with marine growth. And we should be aware, or we should try to combine and to develop innovative solutions in order to take advantage of the wave energy. So I try to present some possible applications or possible utilizations of the wave energy. I could not cover all of them, but there are some with some potential, and we should invest some time working on those possibilities. Some final remarks about wave energy. So we have a lot of patents, so a lot of ideas that were already registered. So solutions to harness wave energy. There are several being presently studied and developed. Some were already tested at prototype scale, so 1-to-1 scale. We have several technologies, and we do not expect a convergence in the near future. Maybe the number of technologies could reduce to only a few, each one suitable for a certain type of application. For application in breakwaters, for application in deep water conditions, for applications in the intermediate waters. So we do not expect a convergence in the near future. We should try to make research, because the experience is not high in this domain, is less than in other areas. The variability of the sea conditions is a very important topic, because as I mentioned before, the technologies should work well for frequent conditions, but they should also withstand the extreme conditions they may face in the sea. And the marine environmental is a very rough environment. We still have limited experience in terms of offshore and maintenance. To have experience, we need more time. And, well, the integration of devices in port and coastal structures, I think, opens new opportunities that should be studied and analyzed. And also the combination of technologies, combination of wave energy with wind, or eventually combination of wave with solar offshore. So we should try to combine in order to have more power and to reduce the cost of the energy produced by marine renewable energies. Okay. it is important to reduce the cost of energy to make this area commercially attractive. And also it is very important to think in a different way, because we usually compare the cost of the energy with the cost of the energy inland, but there are some sectors that operate in the offshore, and the energy offshore is more expensive than inland, and maybe we can utilize energy produced locally to give that energy to those activities carried out offshore. So it's a different way of thinking on this problem. Okay, so from my part, it's all. I don't know if we have any question about this part of the presentation, or if you are too tired after these 5 days of hard work.
Well, I just want to wish you all a great weekend. Thank you.
That was an easy question.
Hi. The Brazilian government, I mean the Ministry of Mines and Energy, and the Energy Research Office as well, they published the early results of the Brazilian Energy Long-Term Plan. So they don't foresee, at least for until 2050, wave energy in the Brazilian energy matrix. Considering you